Okay, so let's try to extend what we proved in the previous section to something more general. Remember, when we have base 10 representation, we have a series of digits and each digit multiplies a power of 10. Now, why 10? Of course, there's a historical reason. You can say 10 fingers, or it's very convenient, but there's really no reason why to use the number that comes after 9 as your base. I could use any number as a base. Okay, so 10 is my base. And when I'm using base 10 representation, then I think of arithmetic mod 10, but I could use any base. And it turns out that for computers, different bases are more convenient, as we'll see shortly. So if I use a different base besides 10, instead of my nth digit being representing dn times 10 to the n, my nth digit will represent dn times b to the n. Okay, so in base b, the digits multiply powers of b. D0 still multiplies 1 because b to the 0 is 1 no matter what b is. But the first digit multiplies b, second digit multiplies b squared, and so on. So if I have the number 6342, base 8 in base 8 representation, the 6 multiplies 8 cubed, 3 multiplies 8 squared, 4 multiplies 8, and 2 multiplies 1. Okay, now you can notice also that in this case, if I want a digit within this representation, I don't want my digit to be larger than 8, because then I get some ambiguity, right? If I had 9, 9 could be represented as 9 times 8 to the 0, or 1 times 8 to the 1 plus 1 times 8 to the 0. We don't want ambiguity. So if we use base 8 representation, then all the digits must be between 0 and b minus 1. In other words, they must be in ZB. Okay, digits must be in ZB. All right. All right. Now, in order to use these base representations effectively, we'll need to be able to convert back and forth between base 10 and these other bases. Okay. All right. Now, the thing is that when we found our digits in base 10 in the previous section, there was really nothing special about 10. Let's go back and see what we did. What did we do to find the digits base 10? Well, first of all, we took the original number mod 10, then we subtracted that from the original number, divided by 10, and then took the result mod 10. Now, instead of using 10, I could use something else. I could use 8, 16, 3,492, however I want to do it. Okay, so I can use the very same procedure, just with different bases. So that's what we're going to do here. Okay, so if I use this if I want to get this number in base 6, now notice that this is in decimal representation. This 137 is a decimal number, but I want to figure out how to represent it in base 6. Okay, so the 1's digit in base 6 is going to be the mod of this, the remainder of this number, mod 6. Okay, so 1 through 7, mod 137, 6, and that gives me 5. You can work that out. Then to get the next one, I would have to take 137 minus 5. Now that has to be divisible by 6 because 5 is a remainder, right? So this number, if I divide it by 6, it turns out I get 22. Okay, and then to get the next digit, I need to take the mod of this number, base 6. Okay, so I need to take the remainder of this mod 6, I get 4. Okay, now I subtract this remainder 4 from my 22. That number has got to be divisible by 6 because 4 is the remainder of 22 mod 6. Okay, so I take 22 minus 4, that turns out to be 18, divided by 6, I get 3. Okay, now 3 is already in Z6, so it's its own remainder. So that means that my number base 6 is 3, 4, 5, right? 5 times 6 to the 0 plus 4 times 6 to the 1 plus 3 times 6 squared. Now this second example goes through exactly the same process. I don't think I need to talk through this. You can read it, make sure that you understand. It's the same process, it works the same way. So it turns out that 121 in base 3 is 11111. Okay. Now suppose I don't want to find the entire representation, but I just want to pick out a single digit from the representation in a different base. Okay. Once again, I can go back to my first section for inspiration. Remember when I did this in base 10, if I wanted to find the 6th digit of a number, In base 10, I took the remainder of that number, mod 10 to the 7th, minus the remainder of that number, mod 10 to the 6th, and divide by 10 to the 6th. Now again, there's nothing sacred about 10. Instead of doing this in base 10, I could do it in base B. So if I wanted the 6th digit in base B, I'd take mod n b to the 7th minus mod n b to the 6th divided by b to the 6th. Okay, so that's exactly what we're doing here. The nice thing about this is that when you're talking about a base other than 10, it's not obvious from looking at the number what the result should be. But my formula still gives me the correct value for the digit in another base. Okay, so if I wanted the 5th digit of this number in base 3, you can't look at this and tell me what it is, but I can use this formula. As I said, I'm going to take, instead of 10, I'm going to use 3. So I take the number, remainder mod 3 to the 5th minus remainder mod 3 to the 4th divided by 3 to the 4th. Okay, so here's some exercises which gives you a chance to practice that. Okay, now why are we so worried about bases? Because actually computers speak in base 2 and not base 10. So you do need to know how to convert back and forth between base 10 and base 2. So some terminology here. In base 2, we don't call them digits, we call them bits. Okay, and 8 bits is called a byte. And 16 bits is not called a mule. So bits and bytes. Okay, so we have this. We can have kilobytes, megabytes, or gigabytes. A kilobyte is 1,000 bytes. A megabyte is 1,000,000 bytes. Gigabytes is 1,000,000,000 bytes. Okay. Now, integers are commonly stored as either 2 or 4 bytes. Okay, so if I wanted to find 31 in base 2, I'm just doing my same old process. Now, notice that any number in base 2 is going to have only 1s and 0s because the coefficients of the number will be in Z2, and Z2 consists only of 1 and 0. Okay. All right, so if I do this process, it turns out that there's only 1, 2, since 31 is 2 to the 5th minus 1, right? 2 to the 5th minus 1. We know that this is going to have 6 non-zero digits, as you can see. But in a computer, you have to store it in a certain space. So if it's stored in as a 2-byte integer, then you would have to store it with 16 bits. So there'd be a lot of 0 bits in front, and then the last 6 non-zero bits would be the binary representation of 31. This is one convention. If you want a binary number, you put 0b in front. There are other conventions as well. Okay, so here this is applying the same algorithm to convert these decimal numbers into binary. Now it's clear this is not a binary number. So when it says express the following, you should assume that these numbers are in base 10. Okay, now another representation that's important in computers is in base 16, because 16 is close to 10, and we can represent a number in base 16. Of course, we only have digits that go up from 0 to 9, but we can add A, B, C, D, E, F. A can represent 10, B represents 11, C 12, and so on, F up to 15. Right? And then we can use a representation using numbers and letters. If you've ever looked at representations of colors in the computer, you may have seen these symbols. That's a mixture of numbers and these 6 letters. Okay. So, for instance, this number, this hexadecimal number means base 16. Hexadecimal means base 16. If I take 0xABCD, remember A represents 10, 11, 12, and 13. A, B, C, D, 10, 11, 12, and 13. Now this is going to be, since we're in base 16, this is D times 16 to the 0. That's D. The C times 16. Now C is what? C is going to be 12, so that's 12 times 16. B is 11, but that's times 16 squared. And then A is 10, 10 times 16 cubed. All right. So, okay. So you should be able to convert back and forth between hex and decimal. Okay, so we've seen how to convert decimal to hex. To convert hex to decimal, it's quite easy. If I want to convert 121, this means that 121 is in base 3. If I don't put a base number here, you should assume that it's in base 10. But if I put a subscript 3 here, that means it's in base 3. Okay, so here that means I have to interpret this as 1 plus 2 times 3 plus 1 times 3 squared. So you just work out the number and compute the answer in base 10. Okay, I wrote 16 base 10 just to make that clear, but this is just the ordinary number 16. Okay, so converting number from base 8. Okay, so you're just using the definition. So that's converting from another base into 10 is even easier than converting from 10 into another base. Okay, so you can be converting back and forth. So in computer graphics, colors are represented using RGB notation, and the colors have different levels. You have different intensity of the different colors. The levels go from 0 to 255. You may recognize that 255 is 2 to the 7th minus 1. 2 to the 7th requires 8 bits. Okay, so that means I can use a 8-bit number, and that's going to be a hex number with 2 hex digits, because 256 is 16 times 16. Okay, so FF is 15 times 16 plus 15. You can work that out, and that's equal to 255. Okay, so when you see this representation here, the first FF represents the red level, so it's a number from 0 to 255. Second FF represents the green level, and the third represents the B level. Now I could have different hex representations. So here I have AA45E2. I can tell by looking at this that the red level is fairly high, the green level is fairly low, and the blue level is actually even higher than the red level. So this is probably sort of like a purple color, kind of bluish purple. Okay, this one here, the 2,9, that means that the red level is fairly low, and the A4, that means that the green level is pretty large, but the blue level again is very large. So this is a bluer color than this one. This is a bluish green color. Right? You can type these into your paint program and find out what the colors are. But here you can associate these hex numbers with colors. And this actually can be useful when you're trying to do things with computer graphics, if you know this translation. Okay, so that's it for this section.